Hey, right. Hey, thanks for coming to this talk. I hope you had a good lunch. So today, with Juan and I are going to talk about how to bypass AM-PPL and disabling the EDRs. So here's the agenda. Right. So we'll talk briefly about who we are, and then I'll cover some endpoint security evolution so far. Then quickly how EDRs can work, just to get the scene set for everyone in the room. And we'll talk about some common modern sort of bypass techniques that are happening today. And then I'll hand over to Juan to get into the research and more detail on how this can happen. Right. Then we'll have some Q&A after. Right. Who we are. So my name is Stephen Coe, based in Australia. I lead the red team at Avast. For those who don't know, Avast is an AV company based out of Czech Republic. But the red team is a sort of global team of guys in Australia, Netherlands, and Czech Republic. So we're kind of split across the different time zones. Juan?
Well, I'm Juan Sacco, co-team lead of the Avast Red team as well. So, to speak to the mic. Sorry, guys. So I'm Juan Sacco, co-team lead of the Red team. So I hope you will like this presentation. Let's see how it goes.
Cool. Just a couple of points on the Avast Red team. So the Avast Red team is internally focused. So it's all about an internal offensive capability. So we basically hack and test things that we use and products that we have. So we do things like red teaming, pen testing, obviously product and infrastructure. We'll do purple teaming, so working with the blue team to make sure that our detection and response works when we simulate known TTPs. And of course, research on various things like this one. So that's pretty much about us. Right. Endpoint security evolution. There's a bit of a historical walkthrough just to get everyone on the same page. So back in the 70s, we started with signature-based antiviruses. So I think the first one's really that's been attributed to Bernd Fix, the German hacker who wrote the first antivirus to detect infected.com files called Vienna. So that's kind of that's when that started. And then as we hit the 80s, a whole bunch of companies appeared. So we're now starting to do some heuristic type AV. So looking at it analyzes the code and how it operates on the basis of experience, so what it's seen before, and then it'll look at to determine if it's malicious or not. So it's an advancement from just pure signature detection. We're now doing heuristics, and in the late 80s, McAfee kicked off. Avira released Antiver, and Avast was founded in 1988, and we released antivirus and secure line VPN. I obviously wasn't working for Avast back then, but yeah. And then we get to the 1990s, we start to see some cloud behavioral stuff, right? So and anti-rootkit stuff. So Dr. Solon's released some antivirus rootkit. AVG released some stuff as well. Bitdefender and Kaspersky also appeared in about 1996. Then in 2005, F-Secure released the Blacklight sort of anti-rootkit tool, and then McAfee in the late 2000s released the cloud-based anti-malware Artemis, and also AVG came up with cloud technology. So we're now starting to see beyond just heuristics, but these endpoints talking to the cloud providers to get better behavioral analysis, with really because the bandwidth starts to get better, and we can do cloud analysis. Jumping forward to 2010, so about the 2010s, 2013, Anton from Gartner coined the term EDR, Endpoint Detection Response. Now we're starting to see real-time continuous monitoring and collection of data from all the endpoints. So, for example, if you think of things like CrowdStrike and Carbon Black, each endpoint has an agent, it collects data, and then sends to the cloud, does analysis, behavior analysis. and also response. So like the CrowdStrike Falcon platform, for example, it's a whole bunch of guys there looking at alerts, and then they can also do action, so response to any known malware detection on your endpoint. So EDR is all that, and then moving forward to today, EDR has sort of evolved into XDR, which is extended detection, meaning it's going beyond just your laptop endpoints. It's going to end server, but it's also going to your network and cloud workloads and email servers and other application servers. So the scope of detection has become a lot bigger. But also with XDR, it's using SIEM-like detection rules and correlation, but also security orchestration and action, and remediation. So automatic remediation with so it has rules to do automatic remediation and shutting off affected clients, for example. So XDR is continuing to evolve, and if you Google that, you'll see people like Trend and Palo Alto saying, hey, this is the next best thing. Right, so that's a quick history. And now, the next bit is just the Windows architecture. So this is a real quick run through. So MS-DOS pretty much had application and resident programs talking directly to the driver. So not multitasking, and definitely quite unstable, because any fault in that program will result in a crash. And definitely no security there. Now, Windows came along and it started to do sort of protected mode kernel that could multitask, but then it still relied on a shared virtual DOS machine. So it's still not the security that we see now with Windows later version. Yeah. So it was in the early 90s when Windows NT 3.1 came out that we first saw this new model of the user mode and kernel mode architecture that's come up. So user mode application runs in that private space in user land. They're all separated, and so that one application cannot access or alter data of the other programs that we're seeing today. And then the kernel runs all the executive functions in processes and memory and threads, for example, and that is abstracted from the user land. So definitely less loose screens of death, because every driver you load in the kernel has to be signed by Microsoft. So it's more security and more stable. Right. So now we've got some architecture set. We now talk about Windows API. So Windows API is that interface through which we can sort of programmatically access and manipulate the system resources, such as your processes and threads and memory, right? So, and how that works is the applications that in the user land or user mode will access the kernel mode resources through functions mapped in the NT-DLL API. Now, let's take you through an example just to walk through it. So, pretending we have, in this example, we have a user land process. So, for example, you execute CMD-exe or whatever program you do, and then what will then happen is to create a process, it will call a function that's in user land to the NT-DLL that's unexported. So, in effect, it will call that API to access that NT-thread-exe function, which then, after some checking, to make sure that it's all cool, then it'll call make the syscall instruction to do something you want, like to affect memory or your file I/O, for example. So that's kind of how a normal program works, in terms of a flow to call the Windows API. Yeah, cool. Right. With that in mind, what is user land hooking? So user-line hooking is the technique used by EDRs and other sort of anti-cheat engines to redirect the flow, and to be able to inspect and jump into that process that we just saw, right? So it's really about injecting a library, hooking to a library that's for all processes that you fire up. And so obviously it will hook common functions that you'll use, right? So if you open a program, whether it's thread creation or manipulation or memory mapping, they target particular and common functions that malwares and other malicious programs will use, so that you can trap those. And these are the common functions that we can hook onto. Now, the most common techniques for hooking is actually replacing the first instruction in the unexploited function in the NTDLL. So typically, it'll be a jump instruction into a routine. Essentially, it jumps into the EDR's loaded library. Now, I've got an example to take you through this. If I can get this working. Yeah. Okay, let's step through it. So, as per that previous example, you open a CMD shell, for example. It invokes this create remote thread function. It goes into NTDLL, and because the EDR has put a hooking function there, the jump instruction takes it to the EDR. So that command that you then run will be inspected by the EDR. So it's kind of man in the middle, I suppose. And then it starts doing either the signature-based analysis or heuristics or behavioral analysis to see that, okay, what you just ran, that command or that XE you're running is malicious or not, depending on what it knows about it. So at this point, it'll either let it go and go to the kernel mode and do that syscall instructions to make it actually run, or it'll block it and say, AV malicious activity detected, stop there. So this is kind of what Windows API hooking is all about. Practically, this screenshot shows an example of what the Avast AV hook library is. So you can see out of this sort of Process Explorer output. ASW hook. Yeah, ASW hook is that hooking function. So, and this is injected into CMD-exe. So, as injected into every process. So from here on, if you were to open or run an executable, this ASW hook will look at it and go, hang on, that's bad or good. So this happens with every process once you have an AV on the system. Right. Now, why would you want to do EDR bypass? Could be a number of reasons. You could be doing a red team exercise and you want to actually evade detection. So you're on the box, you gain, then you escalate the privilege, and then you want to do some lateral movement and load some tools. You want to stay under the radar. So they could be running Defender ATP or CrowdStrike or whatever it is. So that's one thing. You could be testing the actual EDR and AV products to see how effective it is against evasion. So it's important to be able to manipulate these things. Purple teaming, another good example where we work with the blue team to try and fire techniques and exploits and see if they pick it up or not. So a number of reasons why you want to do this. And here's a list of a whole bunch of techniques that's being used out there. And depending on the environment, the language, the version of Windows you're running, there's a whole number of different techniques that you would use to do this evasion. I'm just going to talk about maybe a couple. So direct system calls access. So instead of going through the API, you're actually disassembling the NTDLL, finding out what the actual address to jump to, and then just sort of bypassing the API directly. So just calling it all from userland and jumping directly to the syscall instruction. So that's one technique. SysWhispers is another one. It's a tool that's been commonly available out there. It will generate custom headers and ASM, so that it makes it easier to less manual, automate that process of jumping directly into the Cisco instructions. So in the deck later on, we'll have more information on these techniques. So if you want to read up more. Right, so that's the quick run through on some backgrounds. Hopefully everyone's on a level page now.
Yeah, so now that everyone is on the same page, so basically now understand how an antivirus works, how an EDR typically works, how do they intercept these interactions with the user what it does. So now we're gonna take you to the AM-PPL bypass part of the presentation. So I'm gonna jump some of this because otherwise we will require like 2 hours or more. So I'm gonna take you directly to the good stuff. Yeah, so straight to it. So the process of basically the Protected Process Light, PPL, I don't know if you guys already heard about PPL, Protected Processes, but it's a technology that has been implemented since Windows 8.1. And I'm talking specifically of PPL because PP processes, the history of PP process or protected processes come way back from Windows Vista, and you have been started using it because of DRM protection. So basically, if you had a Blu-ray or something and you want to just watch the movie, this protected process were running as an application itself, but then you weren't able to actually get the content of it. So that's why it has been started as so. So that's the history of it. And then it evolved into these PPL processes. We still have PP processes. I don't know if you say something else, but the most important part of it is that the following actions are available to PPL processes depending on the access level. Unrestricted from others. We'll go deeper into this. But what is important to know is that we cannot, from an unprotected process, we cannot do a process termination. We cannot access virtual memory. We cannot debug it. We cannot copy the description of access to the memory itself, thread interaction, or token impersonation. This one? Okay, choose an example trying to dump the memory of a protected process. So here I'm running. It's too small. I don't have my glasses. Maybe okay. Anyway, so I'm basically here. I'm trying to use one of the sysinternals tools to do process dump, and I'm running a system shell. So with NT system. And remember, the ACL, of course, is still applied. This PPL and PP process, it's just another protection. So ECL still applies. It's just different protection. Okay. So PPL processes, the basics. PPL effectively prevents an unprotected process from accessing protected processes, as I said. And what we cannot do, this is more specific. So PPL prevents memory write read access. So we cannot do that. We cannot load unsigned DDLs into a PPL process. Prevents token impersonation, and we cannot access from non-protected process. Yeah, so it's quite important. So, but what are the access like from other PP and PPL processes? So, meaning now I told you what we cannot do from a non-protected processes, but what can we do from PP and PPL processes? So, a PP protected process can open a PP or a PPL process with full access of his signer type if the signer type is greater or equal. So basically this is the same level. A PPL can open a PPL process with full access if the signer type is greater or equal, and a PPL cannot open a PP process with full access regardless of signer type. So basically PPL is lower. And I have a Microsoft thing from that, so I'm going to show it's easier to understand. But this is basically how it works. This is how basically it's set up. So when you try to interact with one of these processes, you will end up using PS protection, calling into that, and then you will have a type out the designer at the top, and then at the bottom you can see the different type of values that we have for the protected processes. And here is the nice thing to see that we can see on the top left, we have the protected processes and the success levels, the values that they have, and below we have the protected processes, PPL on this case, so PPL instead of PP, and then we have also the access types. higher is better, always. So WinTCB Light is the best one. Yeah, that's the top of the food chain. In the lower, we have the Authentico Light. And the presentation is called AM-PPL, bypass, because it comes from Antimalware Light. And as you can guess, all the antivirus, they use Antimalware Light. Not all of them. That's over the top exaggeration, but most of them, yeah? And not all process they use anti-malware, and you cannot just go and say, hey, I want this process to be PPL. No, you cannot do that. It needs to be signed by Microsoft. Also the DLLs, some of them, if you load, and it needs to be signed, so you need to spend a few $100s to get the sign, and then you can use it. So now, guys, so basically, now you know a little bit of how AV works, EDRs and stuff. You know, we are from the red team. So from a red team. So what we're gonna show you here, I'm gonna take you through a timeline of how to use this. All what I'm gonna show you here is as today working, and I'm gonna show you how to disable EDR, antivirus, get to the top of the food chain, and then be completely undetected by anything, regardless, because it works like that. So what I'm going to show you now is a different type of techniques of attacks. Yeah, I'm going to start with one exploit from James Forshaw from Project Zero, and then I'm going to chain off all of this. I'm going to show you then what is the chain that I ended up using on this scenario, and then after that I'm going to show you the screenshot of how it works and what we can achieve with it and the end result, right? So we're going to go one by one so we understand how they work, and then we go into the practical execution, right? So the exploit. As I mentioned, James Forshaw from Project Zero discovered a vulnerability that the original intent was to do privilege escalation, and could be but this vulnerability itself also could be abused to inject arbitrary code into a PPL process. It's not as easy as it sounds, but it is like that. Yeah? So now I have to explain you on the right side, known DLLs. Anyone knows what a known DLL's handle is? Okay? So known DLL handles, when you run a process on Windows, typically what it's going to do is going to load some DLLs from disk, right? PPL processes, you remember I mentioned that cannot be. So if you want to inject something inside a PPL process, it needs to be signed. Yeah? And how can we bypass that restriction? Well, if you want to go deeper into this exploit, I have all of the links here for each technique and each thing that I use. But basically, the known DLL handles, if you go into Object Explorer from sysinternals, you will see the known DLLs that are loaded into memory as cache, basically, for performance issues. So basically, when you are creating an instance of a process, first it will load the handle of known DLLs, and then from the list that you have on the right, it will load all of the DLLs from there, and if there is any that is referenced, it will just catch it from memory. Performance, so it's faster. So it doesn't have to do boom, 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 and then grab everything from disk, and then you will get a lot of I/O problems. So it's grabbed from there, and these DLLs, they are used for mostly all processes. So basically like that. And yeah, and the good thing about it is that this exploit allows us to inject a symbolic link as a permanent into the known DLLs, and then when the handle is loaded, then what's going to happen is that this PPL process will load your DLL from there, from memory, and then we use a different technique that I'm going to explain later. That is a phantom DLL hollowing. So I'm going a little bit fast so we can do it on time. But let me know if I can go too fast. Continue. So, just recap on this one. Sorry. Here what we get is a DLL in an object on the known DLLs, so we can do this injection. Yeah, the first part of it. How the exploit works. DLLs are only verified when the file is mapped. Yeah? So we cannot inject a DLL from this into a PPL process. When a section is created, this means that if you are able to add an arbitrary entry to known DLLs directory, you can then inject an arbitrary DLL and execute unsigned code into a PPL process. You can use also this just as a bonus track. You can also use this to get persistence, and you can also use it for privilege escalation. I'm using it for a different thing here. How the exploit works. So only protected processes that have a level higher or equal to WinTCB and request write access to this directory are going to be able to load it. Yeah, and there is another restriction that the targets must be a section object rather than the DLL file path. And because this is going to be already, I already mentioned that it's going to be already mapped into memory. Yeah, so because it's already mapped into memory, what we're going to do, we're going to use phantom DLL hollowing. Yeah, if we cannot replace it from this. So once we have the symbolic link pointing into our DLL from the known DLL's objects, if a program loads a DLL named foo DLL, as example, and the section object knows DLL foo exists, then the loader will use the image rather than mapping it the file again. Yeah, and as I'm going to the bottom. The essence of the phantom DLL hollowing is that an attacker can basically hollow the whole DLL from memory, replace it with your content, with the content that you want on the text section, and then load it and then get an execution. It could be a shellcode, it could be whatever you want it. Yeah. And at the bottom, I don't know why it's not there, but at the bottom there is also the article of a phantom DLL hollowing. So, in order to achieve this, in order to execute the exploit, in order to make that symbolic link to work, there is also a restriction. This needs to be run as system. Yeah? But first, to get system, we need to get admin. And we are starting on a computer. Remember, this is a red team exercise. We start with a computer with user access. Yeah? So we use 1, 2, 3 exploits. We combine it, we chain it. This is an example of an exploit. This is using the .NET profiler. So basically, if we have the bug and impersonate privileges, like they come by default, we can use the .NET profiler in order to get an admin label shell, yeah, by abusing of the type of loading from the COM objects of the task scheduler. It will first. So if we replace the environment variables here and we set up our own DLL with that, and you can see it on the second line where we set up here for ctemp test DLL, but I think on the example on the description is using C Windows task. And then we put the DLL there, run task scheduler, we will get a bypass of UAC. This is a very well-known exploit, it's still unfixed. And there are several others that you can use. To show you another one that it can be used to do the same trick, that is basically abusing of the garbage collector of .NET. So from there you can replace something similar, but you can replace the DLL from there and then try to get an execution, try to bypass UAC. So basically what we're trying to get here is after we get user, we jump into admin. But that's not enough. We need to get system. So how do we get system? So first we say we need to bypass UAC. We use .NET Profiler or the task scheduler, something like that, or any of your choice, whatever you like. But then after that, this is just describing how to get system by doing token impersonation. So first we need to locate, in this case, winlogon.exe, could be anything else. Using create tool 32 snapshot, for 32 to get the PID. Then we run say debug privilege. Basically, we need it to debug the process. And then from there, we're gonna get the token of the process that is running a system. Just making a summary, stealing the token, getting the token, copying the descriptor of the token, and then we can create a new thread or assign that token to something, and then we get a system, and we get system execution. And we need system as requirement for the exploit of the known DLL. Yeah? And remember, we are doing this on a full AV, everything totally controlled, EDR on, everything is on. So that's why everything on the code. So all the techniques that I'm showing, they're going to a big piece of code, into a C++ code, and then an application. And then for that, we are using syscall whispers and some other techniques like dynamic pinbook and so stuff. So basically for that, we don't want, before we get into the top of the food chain, we don't want to be detected. So that's why we start using all these bypasses. So basically to keep under the radar until we are there. I don't know if you guys have been using syscall whispers, but it's pretty easy to use. There is it's on the GitHub page. Basically what it does, I think Stephen already explained it, but basically you talk directly to NTDLL. That's it. Your way. And it works. And they choose release a syscall whisper too, so check it out. And it has some cool stuff like randomizing the stuff. So this is the timeline. The timeline of the attack. So this is how it works. First, we start with a target running Windows Defender. I don't choose using Windows Defender, so we don't point the finger to any company. Sorry, Microsoft, we are pointing to Windows Defender, but this is happening with all other AVs that we have tested so far. So it's exactly the same for others. And we are just showing Windows Defender because it's easy. I think it's a one-two punch, but it works with others as well. So first we need a USC bypass. So I already showed you how to do that. Then we do token impersonation of winlogon.exe. In this example, you can do it differently, but it's needed. Then once we have those pre-requirements, we run the exploit for non-DLL. Yeah. After we run it, then we do phantom DLL hollowing. Yeah. So then we have our DLL injected. Yeah. Before doing that and while doing that, basically we do the execution using syscall whispers. Once we have done that, what's going to happen is that we're going to have a process with WinTCP Light with PPL. Yeah. And then from there, it's game over. So we establish a remote shield stream with reverse shell, something. I use exploit pack for that, of course. And then what we're going to do here, because so far we spawned a process with WinTCP PPL Light. But the AV is still running, and everything else is still running. And then we need to kill it. And how do we kill it? I'm going to show you later how do we kill it once we go through the execution. But then we're going to replace some DLLs. There are also other ways to kill it as well. And then we write memory. So basically we corrupt the process memory of it. And the end result is we hide on a PPL process. And now step by step. So I show you already. So I just show you how the techniques works. So if you want to go deeper into each technique, you can. If you get a grip of these PPTs, then you have the links there to see how the attack works and everything. So don't get overwhelmed with the techniques and stuff. It's on GitHub. I already put it there, so you can try it yourself. So the steps. Defender makes use of mainly three components. In the case of Defender. So as MS, MP, and G.exe that is running with Antimalware Light. You see the highlighted there. NIST server, the network inspection service, also running as Antimalware Light, MPCMD run and others as well for the graphical interface and communication with the user. And I'm showing you here, like it's running. Step number 1, we escalate to admin using task scheduler, the first exploit. So from there, we choose basically replacing a DLL not replacing, adding a DLL to see Windows task, and then we call task scheduler, and because the priority on COM objects, we will get an admin shell. This is the .NET Profiler exploit. Now we got an admin shell. Started as a user, got admin. Bypass UAC. Step number 3. After obtaining admin, we need to escalate to system, run the exploit to inject a DLL into a new instance of a PPL process of services.exe in this case. Prior to that, check that everything is clean before and scan it with Windows Filter to see how it is executed. Then we execute it. So we scan it just because to show that it's clean, it's not detected by signature, and also it's not detected by heuristic or behavioral analysis. So it's pretty much clean, and then we run it. And then we get into step 4. You can see here that we have write PPL mem, and then it just created a new instance of a service.exe that is running with the protection PS protected WinTCB Light. So we have it there. And it's also already injected with our DLL. And because the DLL has already been loaded, then we got the shell below. I'm showing you that I got the shell. Yeah. And then, and from there, from here on, we are ready. It's already game over for the machine because no other process except there are no monitoring processes basically that can kill this process or monitor. Or remember, I said a bunch of things about the memory access, how a process can access the type of PPL with the roles and stuff. Well, it's already done here. So it's in step 5, what we're gonna do is to just kill the AV. Yeah. So to kill the AV, basically what I'm doing here is choose, because I have access to the Antimalware Process Light processes, running process with that protection. What I'm doing is just write in memory using syscall whispers into those, and then just writing null, corrupting the process. And there's also a bonus track there. So when you kill the process, you see that it's spawning a new process when you kill the process. It's in red. Look at the protection of that process. So you can inject there as well. Huh? So, but in any case, what? Oh, it's really small. Well, see come closer. Okay. Okay, but from here, what you can see on the screen is basically that we stop the antivirus, so it's not running no more. We stop it by corrupting the memory of the antivirus, but in this case, we did it for MPNG, so basically the engine of it, and then we also do it for the other service, NIS server, .exe. So they are not running no more, but it's a service that is going to try to spawn it again. And from here, you remember we also talk about hooks, and every antivirus will hook into other applications. Because we have control of the memory and we have control of this, we can decide where do we want to go here. So from here, it depends on your red team scenario, the scenario that you are trying to achieve or what you're trying to do, but you can do different things here, right? Here, for us, it was enough to kill the antivirus and prevent the antivirus from running. But you might want to kill the antivirus or inject into the antivirus or the EDR and keep it running. Yeah? Or you want to inject into it and become the antivirus. Right? So you can inject into the DLLs that the antivirus itself is injected into other processes. So you can use the antivirus to inject into other processes. Yeah? Or you can just kill the antivirus, get a copy of the stream of the network, and then keep giving, because it depends on, are they checking the security center? In the case of ATP, are they checking that, are they running an investigation or something if the antivirus is off? Because there is also a keep alive. If the antivirus or the monitoring and everything is off, that will trigger investigation. So you need to decide prior launching this post-exploitation attack what you need to do. But to make it simple, we don't want the antivirus to run again. And in order to achieve that, this is the most basic stuff, and because we have system rights, and we have WinTCB, We can also bypass them. If there is a mini filter or something there, we can bypass it. Yeah? So we can write into the protected folder. I'm saying folder. We can write in the protected folder, and because of that, here what I'm doing, I'm replacing AMP-PPL.dll. That's basically one of the critical DLLs that is loaded from the process that this application is itself. So when it loads, it will just crash. So it will prevent it from getting up again. Even if you reboot the machine, it will crash. And it's no more antivirus there because it will be mapped from disk. Okay, so basically with this, the engine cannot spawn again, it will not work, and the NIS also will be affected. And it says there, who's protecting me? Let's just put it, no one, sorry. Everything is down. So, at this final stage, we have a reverse shell from a DLL injected in a PPL WinTCP Lite process. In this case, service.exe. A new one, of course. This process cannot be terminated. The virtual memory cannot be accessed or debugged from any other process with a lower PPL. Right? So from here, what to do? So from here, there is no way of monitoring this. There is nothing you can do from a SOC perspective, from a blue team perspective. What you gonna do? Call the Ghostbusters. No, but I'm just kidding here. But the real deal here is Microsoft savings criteria for this specific bug. It says that it's not serviceable. That it means that they will not fix it. It's not a bug for them. It's not something that they will take care of. Yeah, even though if you run this from a user land. Remember, we always stay in user land. We always stay in the same ground, into the same ground as the antivirus. So we were always playing the game of user land, never going outside, never going into kernel, nothing like that. No drivers are involved, nothing. Always user land. All right. So as I say there, even a non-admin to PPL bypass is not serviceable issue. All right. Then we have the credits and the POC. We started to get into the end of the presentation. So here you can get the POC to run it. If you trust me, there is a binary there. And of course, all the other techniques that I have used here, code, explanations, and everything. If you want to improve this, maybe you want to change it, maybe you want to do something else. Like I mentioned, there are several paths that you want to take. And most of these techniques, they were prior this, they were used basically to dump LSAS, used to, So you will find all these techniques used for that. In the case of the red team exercises, we want to use it to get a post-exploitation module. Yeah, that's what we like it. That's what we have this different approach. And this is a big thanks to all the people that steal the code from Stack Overflow as well. And thanks, guys. I hope you enjoyed this presentation. And now is the moment of questions if you have.
Yeah, I have a question. So you said you had debug privileges. Test. Yeah. You said you had debug privileges with a normal user account, which shouldn't be the case. And was it a dev machine, or what was the reason you had this?
By default, it comes with debug privileges, so you can do that.
Okay, like vanilla Windows.
Sorry?
Like normal, nothing changed. Like it was not a production machine as it is used.
It's in a production machine.
Okay. And the other thing is, I didn't understand what's the difference between PP and PPL.
So PP are sorry, I went a little bit too fast on that, but so PP are the protected processes. So basically there is a binary thing there to simplify it. It's like, it is protected or it's not protected process. So is it critical or not? PPL has access levels. Yeah? On access levels, I mean the top of the food chain is WinTCP, then on the bottom of the food chain you have Antimalware Light and Authenticode. And there are a few of them on the middle. You can check it on MSDN.
Hi.
Hi.
Thank you very much for your talk. I would like to ask, EDRs usually have multiple processes and services. So even if we manage to corrupt the memories of these processes, from a SOC perspective, would we have like warnings or flags? Did you had flags in your from a SOC perspective?
The problem is that the monitoring is done by the EDR, and if you stop the EDR, then you will not get more monitoring. So that's what I said, that the only monitoring that you can get is the alert that the monitor is not working. And there is this path that you can take, so you can take several paths after you get there. So, and one of them would be to keep sending the monitoring, but not your stuff, not the dark side. To send some stuff like, all is good. All right. Any other questions?
Yeah, thank you for your talk. Just one question. Are you aware of any techniques AVs or EDR uses to try to bypass like people's syscalling by themselves, you know? Like bypassing hooking and then you're doing the syscall yourself. Are you aware of any AVs or EDRs who can detect that?
Yes, there are several ways. Depends on how do you want to detect it. But you can, for instance, an example is using LSAS. If you want to dump LSAS to get the credentials, there are some clever tricks that the antivirus will do. It's not only hooking what is the call to, like for instance, trying to get create tool should set tool should the call. So basically the function I don't get it right now, but it's when you call mini write dump. And then that you can hook, and then you can detect. But if you use Syscall Whipper or something like that, then you cannot detect that. There are some clever tricks like checking the signature of the dump in the file. So if when you get the dump, you get the signature of it. And if someone made a dump, then you can say, hey, why there is a dump? So if I'm in the antivirus, I will say, why there is a dump? There shouldn't be a dump. Boom, delete the dump, and then mark whoever originated that dump as malicious. So there are ways. All right. Thanks, guys.
Thank you, everyone.